Okay. Yeah, I mean, feel free to ask questions or debate during the talk, and I really welcome Jeff's comments and criticisms. If he doesn't kill us, he'll only make us stronger. So, yeah, I'm going to be, I'm going to briefly, because Joyce already did a great job trying to introduce why quantum theory might be useful in psychology. And I'm going to briefly show some empirical evidence, but my talk is really designed to try to tell you once again, Joyce already started this at a more intuitive level, a little bit more formal level, tell you what quantum probability theory is all about, and what are incompatible events, and what are quantum histories. And in this last topic, it's really something new for me, and I hope I have time for this. These other topics I've talked about many times before, but this is a kind of a new issue that I wanted to get into today. But there's a lot of material to cover, so we'll see how far I can get, especially with questions. Okay, so why use quantum theory? As Joyce mentioned, we like that this concept of superposition, it captures what we think is the psychological idea of an indefinite state, feeling of uncertainty. And we like this concept of complementarity that came from William James, was imported into physics by Bohr, and we want to bring it back to psychology. And it's the idea that our judgments and our decisions are really constructed online. They're not just sitting there waiting to be recorded. And we don't have time to talk about this today, but some of my colleagues, like Peter Bruza, Diederik Eretz, are also trying to apply ideas of entanglement to conceptual combination type problems. So let me just show you an example of some evidence that we use to try to motivate our theory. And the evidence comes from what we call, and I had to put quotes on this, because this is this is where we might debate things, but empirical violations of the law of total probability. So, and I'll be a little more clear what I mean by this in a minute, and we can talk about this. But in quantum theory, we call these interference effects. So I'm going to show you an experiment that's designed to be like a two-slit experiment, or an interferometer type of an experiment that they do in physics. But this is a psychological experiment. We call it the categorization decision-making task. And this task was actually invented by Jim Townsend to test Markov models. But we thought this might be also a good task for testing our quantum model, comparing it to Markov models. We have a paper that was published in Journal of Mass Psych in 2009 on this, and we have some more recent work as well. So the basic idea is that people are shown pictures of faces. So they'll see something to focus their attention. They'll see a picture of a face, and in one condition they have to categorize the face as a good guy or bad guy, and then a little bit later they have to decide whether to attack or withdraw, and then they get feedback on the correct category in the decision. And there's two kinds of faces. There's these narrow. Well, in some of our studies we counterbalance this, but in this condition these narrow faces are generally the bad guys, and these wide faces are generally the good guys, and they're not difficult to discriminate. And so it's not hard to tell the narrow faces from the wide faces, but it's a probabilistic task. And so if you see a face from this category with probability 0.6, we're going to give you feedback to say it's a bad guy. Now you make a decision, and the payoff for deciding to attack, you attack or withdraw the bad. You should attack the bad guys and you should withdraw from the good guys. And we give probabilistic feedback there too. So if it's a bad guy, with 0.7 probability will reward you for attacking, but 0.3 probability that will punish you for attacking. So it's probabilistic.
When you ask if I think someone is a good guy or bad guy, you're not asking me my belief, you're asking me a question which I'm either going to answer correctly or incorrectly.
Yeah.
Okay.
I mean, I'm going to show you a face, and then I'm going to give you feedback. So you're going to say, I think it's a good guy, and I'm going to say, no, it was a bad guy.
Saying, does this person have a history or not?
Yeah, but they learn all this from experience. So first of all, we tell them, to begin with, that one category of faces, I think that we tell them the narrow faces are generally bad guys, and the wide faces are, what?
Both.
Yeah, we counterbalance it. And then they learn through lots and lots of training. So the testing is done after they've already learned all these probabilities from experience. Now the optimal thing to do is when you see a narrow face, you should categorize as a bad guy and then attack. That'll optimize. But of course, people probability match. And Jim Townsend was testing Markov models for this type of task. Whoops. Okay. Now, and so the key conditions, this is like the two-hole experiment, you know. In one condition, you categorize the phase first, so that's like you measure, you observe which hole the particle is going through before it hits the detector. So we ask them to categorize it first, and then we ask them to decide to attack. That's one of the conditions. That's this top row here where we categorize first and then decide, just like I told you about. But the other condition, this bottom row, is where you just decide. So these tests are done at the end of training, and they're mixed randomly. And so on some trials, you're just asked to decide. You're not asked to categorize. I mean, the categorization is still relevant because your payoff depends upon, you know, you want to attack the bad guy, so you still need to think about whether it's a good guy or bad guy, but we just don't ask you. So here we're asking you, but here you just have to infer it, but we don't ask you. So here we don't measure your category. Here we're measuring it first. So we're looking at an effective measurement here. And so here are the statistics that we get from one condition. So one condition, we observe the probability that they categorize the face as a good guy or a bad guy. Let's talk about condition on the narrow faces. Let's think about the narrow face condition, because I'm going to show you the results for that condition. But for the narrow face condition, there'll be a low probability that they'll categorize as a good guy. There'll be a high probability they'll categorize as a bad guy. And then we can observe the probability of attacking given that they said it was good, and the probability of attacking given that they said it was bad. So we can observe all these probabilities from each person in the C then D condition. And then we get this result here in the D alone condition, where we just find out whether they attack or not. Now, this next thing here, this is where the total probability comes into play. Now, but here, when we say when we say the law of total probability holds, what we're saying is, well, will the probability of attacking in the D alone condition be the same as the probability of attacking computed from the law of total probability using the CD condition? So if we assume that the events going on in the CD condition are exactly the same as the events going on in the D alone condition, then we expect the law of total probability to hold. But if the measurement is somehow disturbing the system, then these two conditions, we're not going to get the same results from both conditions.
I must be missing something. I don't recognize the total probability formula here.
Yeah. So in other words, like, we can, oh, I see. I got the wrong letter there, that's why.
Yeah, yes. But
This should be A.
yes.
That should be the letter A. Sorry about that. This should be the letter A. So the probability of attacking should be equal to the probability that you say it's a good guy times the probability of attack given you say it's a good guy, the probability it's a bad guy, and the probability of attacking given bad guy. So this should be the probability of attacking. This should be the letter A.
Same
You can find it right above. You changed it right above. No,
Yeah.
right above. It's probability of D.
Yeah, I don't.
It's probability of attack.
Yeah.
You use D
Anyway,
differently.
well, yeah. Anyway, yeah, that's all right. Yeah, kind of. I'm okay. Yeah, but yeah. So, but that's. I mean, this really is a question mark, really, because this is observed under one condition, and this is observed under the other condition. We're asking if they're equal. Now, if all the events are the same, they would be equal. But if the measurement is changing the events, so asking the good guy is, you know, we can compute a probability of attacking here. And of course, the law of total probability is going to be satisfied here. But the question is the total probability we get here is the same here? And if they're not, that's the measurement effect.
But the total probability formula is a direct consequence of the axioms of probability.
Yeah.
What that means is that the axioms are wrong.
Well,
Which axiom is wrong?
Yeah, which axioms is, well, I would say what axiom is wrong is that we're assuming that the events involved, I could calculate the probability of attack here using the law of total probability. And here we don't ask the category and we observe the probability of attack. If the events here are the same as the events here, then this should hold. But it could be that asking this question changes these events here. And so we have different events in two conditions.
Well,
And then what we're saying is the measurements somehow disturb these events.
I guess I had in the previous talk, I had a more basic question, which is what is the sample space that we are talking about?
Yeah, so that's a very good question. So we have a sample space under this condition. It's 4 events. you know, AG, you attack, you say good in attack, good in withdrawal, bad in attack, and bad in withdrawal. Those are 4 events in this space. This space, we only have 2 events, attack or withdrawal. Now the question is, can we relate these two probability, we get a probability distribution across this sample space, we get a probability distribution across this sample space, and obviously this sample space is not the same as this, because we'll see they came out to be unequal. So the probability distribution in this sample space under this condition is not the same as this one. And then we want to build a theory, one theory that'll link together these 2 different sample spaces. That's the idea. Yeah. And now, if you read,
Is there an
yeah.
implicit understanding on the part of the subject that they only attack bad guys?
I mean, they learn that from the experience. During the entire training phase, they're categorizing and deciding to attack or withdraw, and they're getting payoffs. And so this is, after all that training, and now we're giving them these mixed trials. So they're giving categorization and decision, and sometimes just decision alone.
Yeah, but it just seems to me that the probability measure is indexed, at least in some way, by the condition, and it's not being shown.
Well, I know, that's true. You're right. So that's true. We could put these condition on CD, condition on D alone, and that's true. And so we're asking is, do these things match up? And if they don't match up, that measurement somehow changed those things.
But they have different tags.
Yeah, I know they have different
why
tags,
should-
but that's what we want to explain. I mean, why is the 2-hole experiment interesting then in physics? Because the measurement changed the distribution. When you don't measure which hole the particle goes through, you get one distribution, the interference pattern. If you measure which hole it goes through, you get a different distribution. That's exactly the same probability framework I have here. The structure is identical. There's no difference. But what's interesting in physics, why would looking at which hole it went through change the distribution?
To be fair about it, in physics you see something amazing, which is, first of all, you don't get interference. Well, I'm going to say something that could be misinterpreted. It's a statistical distribution.
Yeah.
And so you send a slow beam of particles, like electrons,
Yeah, one
right
particle at a
through
time.
1 or 2 slits.
Yeah.
And gradually, the interference pattern builds up one way or the other.
Well, that's what we do this trial by trial. What's the difference?
And the interpretation is very directly reflected in what you see. But that's not the case here. This
No,
is,
what we're seeing is,
your underlying interference is not seen. Show me the interference.
well, they don't see the interference in physics either. They just get the statistics.
Oh,
They see the interference is this. They don't have to do it with the 2-slit with the continuous wall. They do it with the interferometer, where you just have the particles redirected at one target, and it's exactly the same mathematical framework I put on the previous slide. It's exactly the same interferometer experiments. Yes.
So I just have a kind of methodological warrior question, which is, so if you think that in addition to the underlying probability of representations, there's some additional like response noise, and when you add in the response noise from the different phases of the experiment and combine it, you're going to get some regression to the
Well, that could be a case. And actually, Jay McClellan asked me that several years ago, so we did an experiment I'll show you next that actually addresses some earlier questions. Yeah, I'll get back to that. Mark was talking about a question that kind of gets at the same thing. Anyway, we'll see. Well, anyway, so here we have the results of this experiment. We've done, and I'll show you on the slide, we've done this experiment over and over again, and we get the same type of results. Now, with the good guy face, is actually the total probability works out pretty well, so it actually depends upon the face, which is something that we've been trying to explain with the quantum model. But the good guy face, here's the probability categorized as good, that's probability attacking given it's good, probability categorized as bad, probability attacking given it's bad, and that's the total probability. So all these statistics come from the C then D experiment, and then here's from the D alone. And you know, we do get the systematic small violation in the good condition, but it's pretty small. But we get a much bigger one in the bad guy phase. In fact, what's really interesting here is if you look at the probability of attacking, given that they said it's bad, it's lower than the probability of attacking one when it could be either one. And that's a strange result, I think. Now, this categorization decision-making experiment is one example. We get other results like this in Prisoner's Dilemma game. We get other results like this in gambling games. And so it's not just this categorization decision-making task. So that was the violation of total probability. It's not a violation of total probability. You can condition it on the two distributions, and then you have another. But people like to call it the violation of total probability.
You know, it seems to me now that perhaps you're replacing A with D was a better way than
Yeah.
doing it this way.
Yeah, actually, because then it doesn't confuse the two.
Event.
Yeah, it's a different
It's
event.
not A.
Yeah, so actually, it's better to do it that way. Yeah, it's true. It's better.
It's like
Keeping it,
essentially.
yes,
Instead of
keeping it
indices,
clear.
you're-
Yeah, that's right. I should keep that mistake in there. Anyway, this is just briefly to show you, we've done this experiment counterbalancing and in various variations, and we get the same result. The bad guy faces give us a big violation of total probability here that's highly statistically significant. And here's the interesting thing, to address Mark's question, and maybe address Noah's question too, is instead of asking them to make the decision, now we just tell them the category. Say, it's a bad guy. What's the probability of attack? It's a good guy. What's the probability of attack? And then we don't tell them anything. What's the probability of attack? And we get the same result. So even if you don't make them, they don't have to make a category response. They just see the information. So this is getting at Mark's question, and what Joyce is trying to say, I think, is that it's really a reduction of uncertainty. It doesn't matter if the reduction comes from information or you resolve it yourself. In this case, we resolved it for them. We told them the category. Here they resolved it themselves. Well, anyway, so is there other evidence? And I was just saying there's a lot of evidence from these different fields.
Jerry?
Yeah.
A quick question about that result.
Yeah.
So I would imagine modeling that second one, I mean, I agree, that's cool, and says something about what I asked. I would imagine modeling that by basically saying, look, you condition on that piece of evidence, right? That reduces your uncertainty, and so that's kind of, well within the usual rules of probability. The fact that it matches that one makes me think that you're just treating your action as an observation. But
Yeah, well, believe me, we're not saying that we have the only model for this. I mean, you might be able to construct other models.
I'm
and-
just
yeah,
asking,
yeah.
have you considered that, and is that consistent with the data, or is there something?
I don't know. I'd have to think about it. I mean, we've tried Markov models. Of course, we started with Jim Townsend's Markov model, which basically these violate. And then we've tried some other models, but we haven't. I'm like signal detection model won't work here either. If you assume that the boundaries for the categorizations are not changing. If you assume asking the measurement shifts the boundaries around, then you can explain anything. But if you fix the boundaries, then the signal detection model satisfies the law of total probability that I had up here. Yeah, okay. But we have a quantum model, but it's not the only model. Okay, let me just briefly go back over the basic principles of quantum theory that Joyce was nicely describing earlier. I'll try to do it a little more quickly because I got other things I want to talk about. But yeah, so here we have the left column, we got the classical theory, and the right column, we got our quantum theory. And we're trying to show here that quantum theory is not that strange, really. I mean, and Jeff was asking, where's the quantum? This is our quantum. I mean, these principles that we're using, that's our quantum. We don't have any, what's the constant? We don't have any Planck's constant. We have a parameter that would be the action that we'd have to estimate in a cognitive experiment, but we don't have a Planck's constant. But yeah, so anyway, in your class, and here I'm going to, and quantum theory, as Jeff was pointing out, actually started out for infinite dimensional spaces. Position and momentum, they're infinite dimensional. And then you have infinite dimensional operators, and then there's some subtleties to infinite dimensional spaces that we don't need to go into here. I could present all of this with infinite dimensional spaces. It all goes through. We're using finite dimensional spaces, which, by the way, are used in quantum information theory a lot when you have n qubits. Anyway, so we have an outcome that's a member of a sample space. So we have a sample space composed of points that we might call the outcomes. Those are the atoms. And in quantum theory, you have a vector space. So we're replacing sample space with a vector space. And the outcome, which is a point in our sample space in the classic theory, corresponds to a ray, a basis vector in our vector space. In classic theory, an event is a subset of the sample space. In our quantum theory, an event is a subspace. It could be n-dimensional. I mean, the subspace could be 1, like a ray, or it could be a plane, 2, it could be 3-dimensional subspace, whatever. I mean, in some higher dimensional vector space. And in classical theory, you have a probability function, which maybe when you get into generalized probability theory, they call the state. Anyway, the state is the probability function that assigns probabilities to the subsets of the sample space. In quantum theory, the state is a vector sitting out in your Hilbert space. And we use that one vector to assign probabilities to all the events. And the way we do that is take your state, and for any event, like the event A, we take your state, we project onto that subspace, we get the projection, and then we compute the squared length. And if you like a regression example, it's like doing multiple regression. You might have a large 100-column vector of scores from subjects. You got 2 regressors that are your predictors, and you're getting your prediction by projecting that 100-dimensional vector of scores on that 2-dimensional plane of predictors, and that the squared length of that projection is your r squared. So quantum theory is like using r squared. And to go on a little bit more, yeah.
So those two things on the previous slide, those aren't actually different yet, right? Because
They're not-
probability I can think of as a point in the positive quadrant of the unit sphere.
Yeah, so they're not really different here yet.
Okay.
It's only when you start getting into the incompatible events.
The measurements, there's nothing happening.
Yeah, sequences of measurements. You have to have 2 measurements at least.
When I think of your interpretation of the right column as an r squared,
Yeah.
can you explain where what corresponds to the violation of total probability?
Not yet. I will in a minute, a little bit later. Yeah, so to go on a little bit, so classic theory, suppose we get some information. We learned something about event A is true. Then we form a new probability function, conditioned on A. We take our joint probability and divide it, and we normalize it by the probability of the event A. In quantum theory, we're going to be doing something similar. To get the conditional probability of event X, given that we observed and learned information about event A, we're going to take our state, we project it on to the first event A, and then project it onto the second event X, get that squared length of that projection. Then we normalize by the projection on the event A. So it looks very similar, except this is non-commutative. And so this is where the theories start differing. Because, of course, this is commutative right here. X and A is the same as A and X. But here the order matters. And of course, if the order matters, if these don't commute, that defines incompatible. That's what we mean by incompatible if they don't commute. If they commute, they're compatible. And then you get if they commute, you're going to get the same answer as classic probability theory. So here's the interference. Here's how the interference happens. I mean, this is the basic explanation for all these violations of what they call total probability. Like they get in physics, the 2-hole experiment is the same explanation here. And our experiment that when we model our categorization decision-making experiment, we use this kind of an analysis. Here I'm back to A, so sorry about it. Here I'm back. Here's the probability of, if I was consistent, I would have a D here now. But now here's the probability of attacking under the condition where you only have to decide to attack, you don't have to categorize. So quantum theory says, well, when you're asked this question about attacking, you start with your state that depends upon the face that you saw. You saw some face, it's a bad guy face, you've got some state, and you project onto the subspace corresponding to attacking and get the squared length. Well, we can stick an identity operator in here. This is Feynman's favorite trick, is to decompose the identity. So this doesn't change anything because it's just, it doesn't change anything. Now we can replace the identity with these 2 projectors here, because these 2 projectors are orthogonal and they span the entire space. So this is the probability saying good guy and the probability saying bad guy. You have to say good or bad, and they're mutually exclusive, so they're orthogonal and they span a space. So we replace I here. And then we multiply through here. We get the probability of attacking in good guy times your state, and the probability of attacking, I'm sorry. Oh, this should be a B here. Sorry, that should be a B. It's hard to, yeah. This should be A, G, and psi, A, B, and psi, once we multiply through here. So this is where the quantum theory becomes quantum-like, because we got a sum. Basically, this is a superposition state. So this is where the superposition comes in. Here we have you're superposed between these two possibilities. And then when you get the squared length of a superposition state, you're going to get the first part squared, that's squared length, plus the second part squared, that's squared length. But because you're getting squared lengths, you're getting the cross product terms. And the cross product terms then give you this interference. So that's where it comes from. Now, if things commute, then we can commute this over, and this cross product term just goes to 0, and you don't have any interference. So you only get interference when things are non-commuting. And so this is where the law of total probability breaks down, because the probability of deciding to attack when you don't have to decide the category will be equal to these two terms, which are just like the classic probability, total probability, plus the interference, which could be positive or negative. And so that's how the theory explains these violations. That's how it links the two conditions. You got one distribution when you ask the category first, you got another distribution when you don't ask the category, and then this one state vector, psi, can reproduce both distributions.
Is it supposed to be minus, or am I missing something in the interference term? Because if they commute, minus will give you 0 between the two terms.
No, because this is the conjugate of this one. This is the complex conjugate.
That's sync. Yeah, that's correct.
So what is incompatibility? Then Jeff was asking about this, the abstract idea, but Joyce was trying to explain more the intuitive or psychological idea. But, you know, and this is where I think the psychology becomes important too. And this is where I like to criticize the Bayesian model, by the way, Noah. And the Bayesian model, I mean, maybe you'd say I'm wrong on this. So in the Bayesian model, like if I ask questions about science, you know, do interference effects occur in quantum physics? You know, you can say what's the probability, yes or no to it, you know. Anyway, I can ask you a question about science and get some probability judgment that the scientific question is true or false. So you might have a sample space for science questions, and you know how to assign probabilities to them. But then you might have like a history question. Hadrian Wall was built in 200 AD, yes or no? You know, you can assign a probability to that. But in a Bayesian model, don't you think you'd have to have a joint probability between what's the probability the science question is true and the history question is true at the same time? Yeah. Well, I think that's a lot to demand, that people can have all these joint probabilities. Now let's suppose, so now let's suppose I ask you about the lifestyles of the rich and famous. You know, did John F. Kennedy have an affair with Marilyn Monroe, yes or no? You can give a probability to that. But now you're supposed to have a joint probability between the history question, the science question, and the Marilyn Monroe question.
But you're positing something even stronger, which is a single state vector for every question.
Yeah, but what we're positing, though, is you got a single state vector out there. But for each kind of question you want to ask, you change your sample space by rotating the basis around. And so that's the idea of changing your perspective. So if I'm going to answer questions about history, I use this basis. If I want to answer questions about science, I go to this basis. If I want to answer questions about lifestyles of rich and famous, I go to this basis. So I can answer an infinite number of questions and I can stay in an n-dimensional, finite n-dimensional, large, maybe, let's say 1 billion n-dimensional space. But I can answer an infinite number of questions just by rotating around. And so different rotations represent different perspectives. Here's one other example to get the Bayesians going, maybe. You know, if my friend, I have a friend maybe that's got some kind of a mental illness. You know, I could build a causal model for this mental illness, like the genetics might have caused some kind of problem with the dopamine system, and the dopamine system is causing this kind of behavior. Anyway, I could give judgments for this causal model from two different perspectives. One perspective might be, I'm an insurance agent, and I have to make judgments about probabilities from an institutional perspective. So I can judge the probabilities of all these events from the institutional perspective. But then this is my personal friend's daughter. And so I can judge the probabilities from my personal friend's perspective. And so the quantum model allows you to just change your perspective to judge these probabilities. A Bayesian model would have to have a joint probability that is true from my perspective, and it's also true from the institutional perspective. So every time you have a perspective, you have to change these changes around.
No, I think we need exactly the same thing you need, which is an additional piece of information on the question under discussion.
Yeah, but you're conditioning on another piece of information. When you take out those conditions and you have to fill it out into a complete joint distribution eventually.
This is your show, so it's all.
Yeah, okay. Let's get into dynamics a little bit. So one of the things I want to convince you is that quantum theory is not as strange as Jeff wants you to think it is. If you know, Jeff knows Markov theory, Jean-Claude knows Markov theory. If you know Markov theory, you almost know all the dynamics you need for quantum theory. Just use your Markov theory and take the squared amplitude at the end, and you get quantum theory. It's true, I think so. Now, yeah, so here's a picture of Markov and Schrodinger here. Whoops.
Just if you have time left later, I still do not understand what's that plus thing. I'm thinking
The which one?
somehow this interference term in terms of plus, I'm still having difficulties with that.
Oh.
They could show how it turns into zero if.
Because this turns out to be the real value. This is a complex number, this is a complex conjugate. When you add the complex number with the conjugate, you get the real value, which is going to be the absolute magnitude times the cosine. Now the cosine could go to 0. So it depends on that cosine term.
But the commutativity means simply that the product between the vertical slices.
You can change these orders, and if you change this over here, this will go to 0, so this will cancel out.
Let's just, if A and G commute,
Yeah.
okay, then you can move on the,
Move
on
this
the
one over
left
here.
term, you can move the projector for G through the first A, through the second A. As soon as it hits the projector for B, which is its orthogonal complement, that
Same,
vanishes.
zeroes out.
And the same is true for the other term. So it's okay.
Thank you, Jeff. One of the few times he's going to agree with me. Somebody record that. Well, this is really brief. I mean, this is all finite, of course. We could do this whole thing in infinite dimension, like diffusion models are. This is basically the same principle for diffusion models. Diffusion models are Markov processes, but they're on a continuous state space and continuous time instead of discrete state space. But it's basically the same idea. So, in quantum model, the Schrodinger equation was originally developed for position, which is an infinite dimensional space. But this is what it looks like in a finite space. It just makes it easier. But anyway, in a Markov model, you have a set of states, the possible states that the system can enter. And in quantum model, you have a set of basis states. So the states in the Markov model, you can map each one of those states into a basis state in the quantum model. And you assign a probability to each state in the Markov model. You assign an amplitude, what's called an amplitude to the quantum model. So this could be a complex number that's got a modulus less than or equal to 1. This is a probability between 0 and 1. And then we can take all these probabilities across all the states and form an n by 1 vector. That's the probability distribution across states. And here we can form a vector that's the amplitude distribution across states. So this vector has to sum up to 1, and the squared length of this vector has to be equal to 1, because we're going to use these probabilities, these squared magnitudes for probabilities, so they have to sum up to 1. In a Markov model, we change the distribution by a transition matrix. So we have an n by n transition matrix that changes our distribution. So this is a transition from the column state I to the row state j. And a transition matrix has to satisfy what we call the stochastic property. If you sum across all the rows in a column, you've got to sum up to 1, because you've got to go someplace. From a given state, you've got to transit to one of the other states. In the quantum model, what corresponds to the transition matrix is a unitary matrix. This unitary matrix, it's called unitary because it has this property. It takes its Hermitian transpose by itself, you get the identity. It has to be unitary. Why? It has to be unitary to keep this length 1 and to keep the axes orthogonal. It's got to preserve inner products. So this is the n by n matrix. So this would be the amplitude to transit from the column state to the row state. It has this property. And the probability distribution in the Markov model evolves according to you take your transition operator, apply it to your initial state, and produce your posterior distribution across states. In your quantum model, it looks the same. We take our initial amplitude distribution, apply our unitary operator, and we get our posterior amplitudes across states. This equation for evolution follows what we call the Kolmogorov forward equation. Also follows the Kolmogorov, I should say. Right? Kolmogorov. This is the Kolmogorov forward equation. Well, this equation here satisfies the Schrodinger equation. So this is the Schrodinger equation. So they look very similar. The Kolmogorov forward equation and the Schrodinger equation look almost the same, except for get rid of the I, which maintains unitary property. And this is a Hermitian matrix. It has to be Hermitian for this to be unitary. In the Markov model, this is an intensity matrix. The columns have to sum up to 0 to keep this transition matrix a transition matrix. So they're very similar. I mean, anyway, that's why I'm saying if you look at these equations, they look identical, except you have to convert the amplitudes into probability by squared magnitudes. Anyway, this is just an example. This is a simple example of a categorization decision-making model. It's not actually the one that we're using, but this is one easier to talk about. It stays in a nice two-dimensional space, two-dimensional subspace. It's traveling through a two-dimensional subspace. Anyway, both the Markov model and the quantum model can be related to this diagram. So, we can present a good guy face. Let's see. We can present it like we can present a bad guy face or a good guy face. Let's suppose we present the bad guy face. You're starting here. This is a split, means you have to make a decision. So we present a bad guy face. You can go in a Markov model. You can go down this path where you think it's good and start accumulating confidence across time that it's a good guy face, or you can go down this path here, thinking that it's bad and start accumulating confidence a bad guy face. And then at some point you got to make a decision here. So this is another split. Here you're deciding to withdraw, or here you're deciding to attack. And then we take a measurement here. This is a D alone condition. So the only thing that we see is the measurement. We don't want to ask them to categorize first here. So all these events are going on mentally in the person's brain or mind, and then we observe a decision out here. This will be the Markov transition matrix. It's not that important, but here we're starting from, you present some face and you transit to either the good guy or bad guy face, and when you transit there, you can move over to a higher level of confidence. I just set it equal to 1 here, so you deterministically move there, but it could be transition probabilities here. And then you move over from the good guy, bad guy categorizations to the actions to attack or withdrawal, and change your confidence and attack or withdrawal. I just had it moving deterministically here. And then I just have it reflecting here. You don't have to have it reflecting in the Markov model, but I have it reflecting here, so we go back to the faces. So that's the Markov model transition matrix. The quantum model looks almost the same. So this is a unitary matrix. So you start with the faces, and you can transit over to the good guy or bad guy. You get this minus sign here. This has to be unitary, so this cross product and this cross product have to sum to 0. These columns have to be orthogonal. And they have the sum of the squares for each column has to be equal to 1. And the sum of the squares rows has to be equal to 1. And when you convert the unitary matrix into a transition matrix, the transition matrix has to be doubly stochastic. But anyway, this is the transition matrix for the quantum model. I have a little phase in here. And I know Jeff is going to ask me about this later on. Wait. This little phase transformation in here, that's kind of important for the interference. But here you're going from the face to good guy, bad guy, and then we're doing a phase transition here in a good guy, bad guy, and then we're going to deciding to attack or withdraw, and then we increase our confidence in attack or withdrawal, and then we come back to the faces again to begin with. So the transition matrix, you can build a quantum and a Markov transition matrix. They almost look the same, but they're a little bit different. I put these. I'm going to show you some calculations later from the quantum model. It uses these numbers. They're not that important, but they can kind of fit the results, but it's not critical. Okay. So here in this example, we only know that we're starting here. We presented this bad guy face, and then later this is at time 0. So at time 0, we start here, and then at time, let's say, after time t5, which I haven't listed, after time 4, time t5, we observe a decision that the person makes. So we know we started here, and then we see something over here. And psychologists would like to know, what are the mental events going on in between? And what is the person thinking about in between there? And what does the quantum model versus the Markov model say about those mental events? So that's something I knew I want to talk to you about. So here I'm going into something called quantum histories. This is based upon work by Roger Griffiths called Consistent Quantum Theory. This book's really nice, by the way, because it doesn't require much physics. It's mostly a probability theory book. So what, in Griffiths' book, what's a stochastic? A stochastic history is like a trajectory or a path. So we have a sequence of properties or events at specified time points. So event is some property of the system. Like you might categorize the face as a good guy. Well, that would be a property. Or you might decide to attack. That would be a property.
But mutually exclusive properties?
Well, we're going to talk about properties. The properties, we're going to talk about different properties. Sometimes they'll be mutually exclusive, sometimes they won't.
So height and weight could be.
Height and weight are two properties. They're not mutually exclusive. They don't have to be. But I'll tell you when they are. But they're anyway, we're going to have events that can happen. And now one thing I need to do, though, is I'm going to use a matrix representation of an event. So in the Markov model, you have a set of states. If you decide to attack, what we're doing is we could design a matrix that picks out the state where you attack at a certain time. Because I could ask, what's the probability you attack at time t4? Then the Markov model is going to pick out a probability for the state of attacking at time t4. So we can represent that by an indicator matrix, that event. So an event in the Markov model is going to be an indicator matrix. It's going to be a matrix that's diagonal, and it's going to have ones on the diagonal corresponding to the event that you're interested in, 0 everywhere else.
So
and
this is a continuous time process.
Yeah, it could be continuous time. All these models could be continuous time and discrete state, or continuous time, continuous state. But in this example, it's a continuous time discrete state. In the quantum model, an event is going to be a projector matrix. So the projector corresponds to the subspace. We're going to use a P to represent the event. And then the subscript E tells you what the event is. So like, if you categorize somebody as good at time t2, we're going to have a 10 by 10 diagonal matrix with 0 everywhere except the 1 in row 5. Because at row 5, that corresponds to the state of categorizing good at time t2. Or attacking at time t4, that'd be a 10 by 10 diagonal matrix with 0s everywhere except a 1 in row 9, because row 9 would be where you attack at time t4. That's based upon our Markov matrix, transition matrix, or the quantum matrix, unitary matrix I said before. So we can have this projector for the Markov model, and we can have this projector for the quantum model. Both of them have the same kind of projector. But this is the kind of projector you can have in a quantum model you can't have in a Markov model. So this is the idea of a superposition state. In a Markov model, like Joyce was mentioning before, you have to go from one of your atoms, like you got your Markov model's got a state space. It could be continuous space. You could have a Markov model that's a continuum, but you're going from point to point in that Markov model. And so you're producing a single trajectory across time in the Markov model. In the quantum model, you're not following a single trajectory. You can go through what we call the superposition state. So we're thinking of good guy and bad guy as like basis states, or in the Markov model, those would be distinct atoms in the Markov model. Well, in the quantum model, you can be in a state that's superposed between the two. So you're not in the good guy state, you're not in the bad guy state, you're in a linear combination, in the Hilbert space, you're in a linear combination of the two. And if we start in the unitary operator that I had earlier, if I start at my initial state with the bad guy face, I apply my unitary operator, that's going to create this superposed state. It's going to be some superposition. And then we could construct a projector for this. This is a vector in our Hilbert space, and the projector for this vector is just that vector times its outer product. So that's the projector. So this is describing the property, if you want, of being superposition.
But if it's continuous in time, is there something missing? How do we know?
Well, this is determining the time points.
Wait.
So
how do we know at which time a change is taking place?
Yeah, this diagram I'm putting. I just picked some points out. We could pick as many points as we want.
So it's discrete.
No, it's not discrete, but
Well,
the process could be continuous. But I can only measure it discrete. I can measure it here, I can measure it here, I can measure it
I
here.
know, but we need a rule that tells us when the changes are happening.
No, you don't need to, I mean, you can ask when anytime you want to. You can ask, what is it here, what is it here, what is it here? I can fill a lot of time points in here, like as many as you want. Well, we could even get the whole, in both models, we can get the entire trajectory if we want. I'm just picking out a couple time points. So the process is continuous. I'm just picking some time points out and saying, at these time points, what's the state, or what's the property? So the whole process can be continuous, but you're just picking out a finite number of points out of that continuous process. Yeah. Okay, so here's,
Hey, Jerry, are the complex numbers important? They kind of snuck in at some point from the...
the complex numbers are only important for unitary transformation. And they determine the degree of the interference that you get. Some of my colleagues in quantum cognition don't use complex numbers. You don't have to. You can keep it all real. Some people do. They just keep it all real. I don't know what the advantage of keeping it all real is, so I let it be complex. I mean, the math is the same. The formulas look the same. Nothing changes. You're just constraining yourself to make it real. But if you constrain yourself to make it real, then you're constraining how much interference you can get. And you can't get all the degrees of interference. Okay, so here's an example. So remember, we're measuring at T5. So these are mental events that are going on before we see what happened in the person. So you might say, I'm a psychologist. I like to think about what the person is thinking about before they made the decision to attack. And so you might say, well, there's 5 possible trajectories. They started here. This P0 represents starting with the bad guy face. You could start with the bad guy face at time T0, and then you're traveling along continuously in time. But then we measure you at time T2 and see, and that, well, maybe at time T you're in the bad guy face. You're categorizing as bad guy. And then you're traveling along in time, and then at time T4 we measure you. We ask is the property that you're in the state of attack. So we don't, actually I shouldn't say measure, the word measure here. We're just saying, are you in this property at this time? Are you in this property at this time? So we're asking, are these properties existing at these time points? So this will be one trajectory, that's another trajectory. We have 4 trajectories, and this just completes. So each of these trajectories is mutually exclusive. They're mutually exclusive because, this is going to multiply out to give you 0 here, and this is going to multiply out to give you 0 here. So these are all mutually exclusive trajectories. And they're exhaustive because if we sum across these trajectories, we get all the possible. It's exhaustive. Now the question is, Markov, what the question is, will the mathematics of Markov model permit you to talk about this? And the answer is going to be yes. You don't observe any of these things, but the actual mathematics allows you to postulate them. But when we take the quantum model and we ask, will the mathematics, not the philosophy or anything, just the pure mathematics allow you to talk about this? And we'll see the answer is no, it will not. You can't talk about these mental events. Doesn't make sense. Yes?
Are you assuming homogeneous Markov?
No, it doesn't have to be homogeneous. It can be any transition operator you want in between. It doesn't have to be continuous. Yeah, so anyway, these are mutually exclusive and exhaustive. It's a mutually exclusive and exhaustive decomposition of the history space. I mean, there's various ways to do it. I could fill in more time points here and look at even a more refined history. Okay, so this is a little bit of math, but we're almost finished with a lot of the math. But so here's the probability of the history. So this is one history. You start out some initial state, and at time T2 you're in a property that you think it's a bad guy, and then at time T4 you're in a property that you think you're going to attack. And here's how the Markov model, we want to assign a probability to that history. So the Markov model is going to start with your initial state distribution, apply your transition operator, which is right here, which could be non-stationary. We do your projection in the Markov model, just pick out the states that are relevant for the bad guy. Then we do your transition operation, then we pick out the states for the attack. And that'll give us the probability that you start here and think it's a bad guy at time t2 and then attack at time t4. Griffiths likes to call this K. He calls it a chain operator. So this is the chain operator. Now this is going to be a vector when you finish, because when we're finished, these are matrices, that's a column vector, so it's a vector. This chain operator for the Markov model is linear. We're not going to check it, but it's a linear operator. Now we get the probability from the Markov model by a linear operation. We basically sum across the states. So the Markov model stays linear all the way through. Everything's linear all the way down to the probabilities. The quantum model almost looks like the Markov model. We just changed this from P to psi. So we start at the initial state for bad guy face. We apply our unitary operator. We ask, are you categorizing as a bad guy at time t2? Then we apply our unitary operator. And then we ask, do you want to attack at time t4? So that's our chain operator for the quantum model. This is linear, just like the Markov model. But the probability is a squared magnitude. It's nonlinear. This is where some issues come up for quantum theory about talking about mental events that you don't observe. Okay, so suppose we have some kind of decomposition of the history. This is orthogonal to this, and they sum up to be exhaustive. So we have a decomposition of the history space. What Griffiths wants to impose, which I agree, which makes sense, is that if you have two histories or two mutually exclusive trajectories, the probability of the union of the two, which in quantum theory would be summing up the two projectors, the probability that either history occurs should be the sum of the two probabilities. In fact, I think we would want this if we wanted to get a probability theory like De Finetti's or an additive probability theory. We want, if these are orthogonal, then the probability weight that we give to the sum should be the sum of the two probabilities. So that's something I agree with Griffith. We should have that. We want to cohere, otherwise the probabilities are not going to add up right. Or the probabilities that we assign the histories are going to add up to crazy numbers. So we can't have a sensitive probability theory without that. Now, this additivity follows immediately from the Markov model. So the trajectories I showed you are fine. They have to, because we're going to assign a weight to each one, and they're going to sum up to unity. Any combination is going to be additive because it's all linear. So that history I showed you before is perfectly fine with the Markov model. But the quantum model, in order to give you a coherent dynamic theory, has to impose one additional constraint. These chain operators have to be orthogonal. That's because that's squared length. When you get a squared length, you're going to get the squared value of the first one plus the squared value of the second one, and then the inner product. And if you want your probabilities to sum up to one across the orthogonal histories, then this chain operator has to be, for one event and another event, they have to be orthogonal. So this is what Griffiths calls the consistency requirement. And that imposes conditions on what you can talk about. So here we are, we're measuring the decision at time t5. These are all mental events we want to postulate. So here I'm using just quantum theory. The Markov theory doesn't have any trouble. But if I look at the chain operator here and compute the probability for this history, it's 0.42, using those numbers I showed you before and using the diagram. Anyway, these are the probabilities that we would get for each individual history that we talked about in that decomposition earlier. But this collection, this decomposition of the history space is inconsistent. It doesn't give you consistent probabilities. For example, these two chain operators have a negative, well, they have an inner product, which is a complex number, but they have an inner product, non-zero. This has to be 0. For example, if I compute what's the probability that this or this happens, it turns out to be 0.8, which is greater than the sum of these two probabilities. That's because of that interference effect. So this provides a nonsensical collection of histories. So Griffiths would say you cannot talk about these mental events going on if you want to be mathematically consistent. Nothing to do with philosophy. It just doesn't make the probabilities don't add up in a mathematical sense. It's not a sensible mathematical probability theory. Now, here's another decomposition of the identity. So this is a decomposition where you start with some initial state you go through the unitary operator and you're in a superposition state here about good and bad, and then you go through the unitary operator and you're in a superposition state with respect to attack and withdrawal, and then you decide to attack at time t4. Well, and this is one history and this is the other history. These two are orthogonal because this last projectors are orthogonal, and they're exhaustive. They span the entire history space. All the other possible trajectories that we can imagine are going to have 0 chain operators. So this is a consistent. So this is a description that we can use. Now this is not the only one, actually. So another thing that Griffiths points out is there's more than one way to describe history, and some of them are mathematically equivalent. So I could write another history that's not this one, but it's also perfectly sensible. But the earlier one is not sensible. So we can talk about the brain going through these states or properties, but we can't talk about the mind going through the earlier properties. But let's suppose we put so what happens with measurement? What's happening with measurement is that we're putting another detector in here, so we get detectors here and here. Once we put the detector in here, what happens is we're going to be orthogonalizing. We're not going to be indecisive or indefinite about which path is going on here. We're going to know which path they went down. So that puts a new, technically, we're going to have a tensor product between the measurement basis and the system basis. What happens then, and I know I'm running out of time, so this is my last slide. If we include this category measurement, then we have like the properties of the system I'm indicating here, but this is the property of the new measurement that we built into by the tensor product. So now we can talk about these 4 histories because the measurement is orthogonalizing all these paths. So these 4 paths are now orthogonalized, and now that makes a consistent description. So introducing the measurement, then it gets rid of all the interference effects and produces a classic probability result. So I think it's interesting that, what I want to do is conclude here. Quantum theory provides an alternative framework for developing probabilistic dynamic systems, as Joyce was mentioning earlier. It's very similar to the Markov theory, except you take the squared length at the end. Now, Markov theory allows histories that describe transitions from one basis to another, whereas quantum theory allows for histories that include superpositions. So that's a unique kind of transition that is allowed in the quantum theory, not in the Markov model. And when we're building a quantum model for mutually exclusive and exhaustive set of histories, you also have to check the consistency property to get a sensible probability theory. And if we adopt this quantum mathematical framework, then that consistency property places mathematical constraints on what we can say about unobserved mental events. And it's nothing to do with philosophy. It's just pure mathematics. Do you want a sensible mathematics or not? So I don't have a good joke like Jung does, Joyce does. I'll advertise my book here. Thank you very much for your attention. No, I'm finished. So.
Is there some reason that you give besides mathematical reason why we should think of mental events being different than ordinary events in terms of their logical structure?
I got something. Is another reason other than mathematical?
Yeah, other than mathematical, why?
Well, I mean, see the reason, okay, yeah, there's other reasons psychological. But people think the psychology is bullshit, so then we give them mathematical. I mean, I think it's perfectly reasonable to think that somebody's, like, if I don't have to, like, if I see a face and you're not asking me to categorize it, I don't have to bother resolving the uncertainty about the category. I can go from the face to the decision. And I can go through it being unresolved, which means indeterminate or superposed on the issue of is it a good guy, bad guy. So that means, well, here, let me give another example. Take my son. Take my son. My son did some kind of action. I always like to give this example. He's a good boy, but anyway, let's say he did some action, And you can ask, is it true or false that he did the action? And you can ask whether it's good or bad. And let's assume true and false is mutually exclusive and exhaustive. Assume good and bad is mutually exclusive and exhaustive. Now, I can ask you, is that action my son did, was it bad? And you can answer that question. Now, I'm saying that you can answer that question that it's bad without going through a path where you think it's true and bad, or without going through a path where you think it's bad and bad. You can go through a path that doesn't require you to resolve whether it's either one of those things. That's the intuition. And what the mathematics is saying, if you're not observing, that would make it a sensible set of histories. The history where you think they did resolve that doesn't produce a sensible set of histories.
But it seems like you just take those different paths. Just the way you said it, that I could just think about it as ordinary events, right?
Well, you think so, because you've got a classical Boolean logic brain. But I can think about it. I can think my son, did my son do something that bad? And I can say, no. And I don't have to worry about whether it was true or false. I just say no. I don't have to resolve that issue. And I didn't pass through whether it was true. I didn't pass through whether it was false. I just went straight to that decision.
How would that, how would you deal with your teenage son now in court? And the judge asks you.
Then I have to resolve it. Then I might have to do some home investigation to resolve it. But
Wow.
yeah.
So in classical terms, it would be just if you go by a certain trajectory, in the process you change the conditional probability for the final event, right? So your quantum language allows you to circumvent saying that. You simply say it as a different thing.
Yeah, I mean, you can go from the starting state to the decision to attack without resolving. It doesn't have to go through a good state or
I mean,
bad.
your example was true, false, and bad.
Yeah,
negative.
yeah.
I mean that, people who would think about true or false before they say bad and good.
Yeah.
They, in the process of thinking about good and bad, in classical terms, would change the probabilities of saying.
Yeah. So if you somehow convince them, you'd have to. I don't know how to do that, but you wouldn't be measuring, but you wouldn't say, don't tell me your answer. This gets in an important issue. I mean, Jeff kind of got into this with me on one of my papers. What is measurement? Physics, we know what a measurement is. We have equipment there and everything. In psychology, yeah, you're asking what is a measurement, because when I make this decision, I could say, is this bad action? Did my son do it? And I don't have to report it to you, but I might go through the resolution process. And I might resolve it in my mind, no, it's not true, and it's bad. Or I might not resolve it. And so how do we know if I did this resolution or not? Because we have this, as humans, we have this ability to ask ourselves the question. In physics, the human being has to ask the particle the question. But human beings can ask themselves a question. So we might ask ourselves a question and resolve our uncertainty and what they call in physics collapse, or some people don't like that word really too much anymore. You could collapse yourself or leave yourself indeterminate. And that's a good question. I mean, when do people do a self-measurement and resolve uncertainty versus don't do the self-measurement? I don't know.
Would there be an example?